Title of the paper:
Inclined magnetic field and nanoparticle aggregation effects on thermal Marangoni convection in nanoliquid, a sensitivity analysis.
Authors of the paper. Details of the paper.
This video presents fact on
The concept of nanoparticle aggregation, and the theoretical and empirical reviews of.
If you like our videos, kindly subscribe to our channel.
We share
Theoretical and empirical reviews.
It is all about learning research facts and sharing with others.
Please subscribe to our channel if you like our videos. Before we present the theoretical review, let us consider a preliminary introduction. The control, growth, and formation of nanoparticles to form clusters either by particle transport mechanisms or an interfacial chemical reactions are known as the aggregation of nanoparticles in the base fluid.
But, is there any force responsible for such clustering?
The nanoparticles do not exist as individual particles in the fluid medium but tend to aggregate together due to interparticle forces.
So, what is the relationship between interparticle forces and distance between those tiny particles?
According to Kiley, 2016, interparticle forces are inversely related to the distance between the particles, which is in turn partly dependent on particle shape.
According to some scholars in the year 2001, they established the fact that the attractive force increases when the particle size decreases.
Whether or not the interparticle force is repulsive or attractive, Huo et al. 2011 concluded that the magnitude of interparticle force is dependent on
A. The geometry of the liquid and solid. B. The wetting angle. Aggregation of tiny particles in the base fluid was described by some scholars in the year 2014 as a factor capable to alter the physicochemical properties, reactivity, fate, transport, and biological interactions of nanoparticles.
How do we know that aggregation of colloidal particles in the base fluid have occurred?
Aggregation of colloidal particles in the base fluid has occurred when
A. The physical processes bring particle surfaces in contact with each other.
B. There exists a short range in thermodynamic interactions, and
C. Particle-particle attachment occurs.
stability is one of the crucial factors that are accountable for the overall benefits as well as for the heat transfer augmentation of the hybrid nanofluids, since the presence of nanoparticles determines strong van der Waals forces, thus creating aggregates.
according to Ali, 2020, some of the advantages of the single-step method of preparing hybrid nanofluid are
A. Very good stability.
B. Nanofluid homogenization.
C. No particle aggregation.
The last point is true because interactions in the transport of nanoparticles, as in the case of nanofluid made up of a single-step method, may cause the nanoparticles to adhere to each other and eventually avoid nanofluid homogeneity. Ali, 2020.
But it is difficult to prepare a homogeneous nanofluid with proper stability without particle aggregation. More so, evaporation of the fluid is a factor causing the aggregation of nanoparticles.
There is another question we need to consider. What exactly do we know about the effect of nanoparticle aggregation in unstable nanofluids?
In a study on the thermal conductivity, electrical conductivity, viscosity, and refractive index of two non-aggregating, stable, nanofluids of gamma alumina and silica and two aggregating, unstable, nanofluids of titania and alpha alumina by Angay Arcani and Philip, 2014, it was reported that the effect of aggregation in unstable nanofluids leads to a strong modification of their viscosity and refractive index.
What are the types of nanoparticle aggregation?
Homoaggregation and heteroaggregation are two types of aggregation. Homoaggregation refers to the aggregation of two particles of the same kind, while heteroaggregation refers to the aggregation of dissimilar particles.
Homoaggregation under controlled laboratory conditions produces aggregates of reasonably predictable fractal dimension, whereas heteroaggregation typically forms natural fractals. making aggregation states more difficult to describe and predict. Keller et al., 2010. Homoaggregation under controlled laboratory conditions produces aggregates of reasonably predictable fractal dimension, whereas heteroaggregation typically forms natural fractals, making aggregation states more difficult to describe and predict. Keller et al., 2010.
Smaller particles aggregate more readily than larger particles because aggregation lowers the free energy of the system. Besides, the smaller the particle, the higher the surface energy.
Results obtained by Marangoni 2019 show that incorporating aggregation into the transport model improves the predictiveness of current theoretical and empirical approaches to nanoparticles deposition in porous media.
More so, disregarding the acceleration factor, aggregation enhances nanoparticles' mobility at regions close to the injection point at a field scale and causes their retention at greater distances through alteration of their diffusivities, secondary interaction energy minima, and settling behavior.
Is it possible to disregard the acceleration factor?
He et al. 2007 included the aspect of nanoparticle aggregation in the heat transfer analysis of titanium nanofluid in a pipe and discovered that the viscosity increases with nanoparticle aggregation.
Next, we shall now present the theoretical review. Marangoni and Marangoni, 2021. Compare the dynamics of ethylene glycol conveying aggregated and non-aggregate titanium nanoparticles due to Marangoni convection along an inclined wall when Lorentz force, thermal radiation, space, and temperature-dependent heat sources are significant.
Next is to present the empirical review.
The results of Marangoni and Marangoni, 2021, show that
1. Increasing Lorentz force, angle of inclination, and volume fraction made the velocity of the transport phenomenon to decline, but the velocity without aggregation is higher than the velocity with aggregation. This is true because the presence of nanoparticles determines strong van der Waals forces, thus creating nanoparticle aggregation, and nanoparticle surfaces are in contact with each other, thus forming a kind of block that reduces the distance cover per time.
2 et al. The chosen level of Lorentz force and volume fraction. It is obvious in the results that the temperature distribution in the dynamics of ethylene glycol conveying aggregated titanium nanoparticles is higher than that of non-aggregate of nanoparticles. This indicates that not only does aggregation enhances nanoparticle mobility, but the associated particle-particle attachment causes additional internal heating. Marangoni, 2019. More so, van der Waals forces are independent of temperature except for dipole-dipole interactions.
Special thanks to all the editors and reviewers of Chinese Journal of Physics, Elsevier. We share to appreciates the contribution of the authors to the body of knowledge.
We share.
theoretical and empirical reviews.
It is all about learning research facts and sharing with others.
Please, subscribe to our channel if you like our videos.